In this video, we solve another Bernoulli differential equation. This is problem 22 from section 2.5 of the ninth edition, of the Zill textbook. It's called A First Course in Differential Equations with Modeling Applications. This is the differential equation. We've also got an initial condition. Notice that you have a coefficient involving y multiplying the derivative, and you also have this y to the 3/2 power over here. So on the surface, you might think that this isn't a Bernoulli differential equation, but remember what Bernoulli differential equations look like. If the differential equation can be written in this form, dy dx plus a function of x times y equals a function of x times y to the nth power, where n is not equal to 0 or 1. If we can write the differential equation this way, then the equation is a Bernoulli equation. So as soon as I see that y to the 3/2, I'm thinking about that y to the n. This equation needs to be rearranged a little bit. So I need a coefficient of 1 in front of that dy dx in order to get this differential equation in that form. So we're going to start by dividing this equation by y to the 1/2. So this is our original dE. I always like to label them on the left-hand side of the page and then write out my steps on the right-hand side. So we'll divide everything by y to the 1/2 and then simplify. So we have dy dx here. And then remember with this piece, got this fact, a couple of different facts. If you have a power raised or divided by another power, that's the same as x to this power minus that power. You subtract the exponents. So we're going to subtract the exponents here. 3/2 minus 1/2 is 2/2, or just 1. And then we have this y to the negative 1/2 on the right-hand side. So now when I'm looking at this and I'm comparing it to this, I see that this is a Bernoulli differential equation. I've got the first derivative of y with respect to x plus a function of x times y. The implied function of x is just a 1. And the implied function of x over here is also a 1. And we've got a y to the negative 1/2 power. So this is a Bernoulli differential equation with n equals negative 1/2. So we start by writing the dE in this form. And then after we have done this, then we let u equal y to the 1 minus n. That's how we solve Bernoulli equations. Bernoulli said, if you let u equal y to the 1 minus n, and n in this case is negative 1/2, so we have 1 minus a negative 1/2, or 1 plus 1/2. That's y to the 3/2. And then if you compute du from this, or excuse me, not du, the derivative of u with respect to the original independent variable, which is x. Since y depends on x, the derivative of this piece is 3/2 times y to the 1 less power. 3/2 minus 1/2. Or excuse me, 3/2 minus 1 is 1/2. So we do that, we use the power rule there, and then we multiply by the derivative of the inside. You can think of that as coming from the chain rule, or you can think of that as coming from implicit differentiation. So we let u equal that, and then we compute du dx. And then we notice that we've got a coefficient of 3/2 times y to the 1/2 in front of that dy dx. So we're going to take this differential equation, which is in this form over here, and we're going to multiply it by this. I'm going to call this differential equation dE star. So that's the differential equation in this new form. And take dE star and multiply by 3/2 y to the 1/2. And then you want to simplify. When you simplify, the resulting expression should be a linear differential equation in U. This is equivalent to this. Since U is y to the 3/2, this piece right here, this whole thing, is du by design. That's why we multiplied by this. I keep saying du. It's du dx by design. We multiplied the differential equation by this term right here, so that this whole term would be du dx. So that is du dx, which is good. And then over here, we've got a 3/2. And then we have y to the 1/2 times y to the 1st. Add the exponents, that's y to the 3/2. Well, that's the same as u. Also by design. And then on the right-hand side, you should have that y to the n and the y to the negative n. They cancel. The y to the negative 1/2 and the y to the 1/2. Add the exponents, it's y to the 0, which is just 1. So we have this here. So this, after simplification and after substitution, this is a linear differential equation in U. Then we just solve this linear differential equation using an integrating factor method. It's not solving, solve. Okay, so whenever we're using this integrating factor method, we always identify p of x. P of x is the function in front of u. I'm going to call this dE double star so that I can refer back to it later. So we identify p of x. We compute the antiderivative of p. And then we define the integrating factor to be e to that power. So the antiderivative of 3/2 is 3/2 times x plus a constant. We're going to choose for that constant to be 0 because we only want one integrating factor. We don't need infinitely many integrating factors. We just want one function that we can multiply by. So we'll just let that c be 0. Then the integrating factor is e to this power, where c is 0. Then Bernoulli said, if you take that differential equation in standard form and you multiply by the integrating factor, then something very nice will happen. So I've got dE double star here. And I'm multiplying every term by e to the 3/2 x. So you're just multiplying by the integrating factor. Now, if you've done everything correctly, the expression on the left-hand side should be the derivative with respect to x of your dependent variable, which in this case is u, times the integrating factor, which was that e to the 3/2 x that we just multiplied by. So that's one of our steps. We recognize the left-hand side as the derivative with respect to your independent variable of your dependent variable times your integrating factor. And let's check it out, make sure it's true. This is a product. This is a function of x times a function of x. So when I take the derivative of this, I've got to use the product rule. I'll call this my first function and that my second function. It's the derivative of the first times the second, which is right there, plus derivative of the second times the first. Well, the derivative of e to the 3/2 x power is e to that power times the derivative of the inside. Derivative of the inside is 3/2, good. So we've got derivative of the second times the first, which is u. So yes, it does check out. And that means we're 2 steps away from getting u by itself. We want to undo operations. This outermost operation here is the derivative. So to undo differentiation, we anti-differentiate. So we're anti-differentiating both sides with respect to the independent variable. In this case, that's x. And then on the left-hand side, we just have u times the integrating factor equals this integral over here. So we bring the 3/2 down, and you have e to the kx. The antiderivative of e to the kx is e to the kx divided by k. And if k is 3/2, we're dividing by 3/2. And dividing by 3/2 is the same as multiplying by 2/3. So you flip it and multiply. Don't forget your c. These guys reduce. And we just end up with an e to the 3/2 x plus c over there. So u times this equals this. We've anti-differentiated both sides. Now we're trying to get u by itself. So we'll divide everything by e to the 3/2 x. And you can do that term by term if you want to, but just make sure you also divide the c by the e to the 3/2 x. If you don't, you're going to get the wrong answer. So these guys reduce. These guys reduce, and you're just going to have a 1 there. There's an implied 1. Just divide by the integrating factor to get u by itself. And we end up with this over here. We have u equals 1 plus c divided by e to the 3/2 x. Well, I can bring that up to the numerator if I change the sign. So that'll make that e to the negative 3/2 x. Now remember, u is just something we made up so that we could solve this problem. So now we have to back substitute. So we're trying to get a function, y, that satisfies the original differential equation. U was originally defined to be this y to the 1 minus negative 1/2, or y to the 3/2. So you have to replace u with y to the 3/2, because that's what it is. That's what it was when we defined it to begin with. So u is y to the 3/2. And you're trying to get y by itself. So to isolate y, I'd really like this to be a y to the first power. I'm going to raise both sides to the reciprocal power. Since that's 3/2, we're going to raise both sides to the 2/3 power. Those, when you multiply those together, you're going to get y to the first. And we've got this. So you have 1 plus c times e to the negative 3/2 x raised to the 2/3 is equal to y. And in general, you're just going to raise both sides to the reciprocal power of whatever power is there. When you do that, those will multiply, and you're just going to get a y to the first. Now this is a family of solutions. The original differential equation was nonlinear, so there's no guarantee that this is a general solution, but it is a family of solutions. And we were actually given an initial condition this time. So if we were just asked to solve the differential equation, we would get that family of solutions and be done. But we're not. We're actually asked to solve this IVP. So we know that when x equals 0, y is supposed to be 4. We want the solution curve that passes through the point x equals 0 when y equals 4. So we'll use this to find the value of c. So we have y of 0 equals 4. And let's translate that. That means that when x equals 0, y has to equal 4. So to find the right value of c that makes this statement true, I'm going to replace x with 0. And e to the 0 is 1, of course. And that's what we get. We get 1 plus c raised to the 2/3 power is y of 0 in general. But we want y of 0 to be equal to 4. So we set this equal to 4 and we solve for c. So I've got 1 plus c to the 2/3 power equals 4. And I want to get rid of that 2/3 power. So again, I raise both sides to the reciprocal power. So I'm going to raise both sides to the 3 halves power. Then that times that is 1, and we just end up with a 1 plus c on this side. And over here, it helps to remember this fact. Whenever you have a number raised to the n over m power, so you've got a rational exponent, that's the same as the mth root of x raised to the n. You could also do x to the n and then take the nth as well. So this is another possibility. But I think that when we're doing this with numbers, it's better to do it this way, because if you take the nth root first, then it'll make a small number and then you just raise it to a power, as opposed to taking a number, raising it to a power first, and then trying to take the root of a larger number. So let's take this and rewrite it this way. That 2 in the denominator tells me I've got to take the square root of 4, and then we want to cube it. Square root of 4 is 2, 2 cubed is 8. So c is 8 minus 1, which is 7. All right. Now you're not finished until you back substitute. So we had a family of solutions. Now we want a particular solution. We want to back substitute c equals 7 into the family of solutions to find the general solution. So we've got y of x equals a 1 plus c, which is 7, raised to the e, or times e to the negative 3 over 2 times x, all raised to the 2/3 power. And this function's well-defined all the time, because this exponential is just a positive number. We're taking a positive number, multiplying it by 7. And this says take the cube root of this result, which is just a positive number, and then square it. Well, you can take the cube root of anything, and of course you can square anything as well. So this is well defined for all real numbers. So if I'm just looking at this and I'm thinking about the domain of this function, the domain would be all real numbers. Let's look back through the method and see if there's any other restrictions on x. Well, we know that y can't be 0 because we were dividing by that there. Okay. No restrictions on x here. The exponential can't be 0, but exponentials are never 0, so we're fine there. Yeah. The only concern is that y might be 0. Well, actually, this function will never be equal to 0, so we're good all the time. So it looks like this is our particular solution, and it's going to work for all real numbers. That's our interval of existence. So you have the particular solution, or PS, on an interval I, the maximal interval of existence.